Hello everyone, we're going to go over some examples for usage of MATLAB for control applications. It is easy to obtain the response of a linear time invariant or LTI system with MATLAB. We dive into the examples right away. Consider the simple second-order linear model with an input-output equation y double dot plus 3y dot plus 12y equals 0.8 u, where you have y as your output and u as your input. For this system, we can form the transfer function gs as 0.8 over s squared plus 3s plus 12. That is the output in the Laplace domain over the input over Laplace domain. That's the definition of the transfer function gs. Now, to be able to plot the response of the system to different types of inputs, we have multiple options. We want to first see the response of this system to a unit step response or a unit step input. We can use two options here. There may be other ways, but we're going to discuss two options here. Option one is to use the built-in MATLAB function step.m, which you can directly use with step in MATLAB. So here will be how you can actually form your transfer function and then show the input response in MATLAB. Each line of code has its own descriptions or comment that tells you what each line is doing. And we're going to try to type these commands in the MATLAB and try to run them and see what we get. So let's go to MATLAB. I have already opened the script file and I have saved it with the name examples.m. So we should be ready to start writing our code and running it. So for this one, we had a transfer function that had the numerator as 0.8. So I'm going to define numg for the numerator as 0.8. I'm going to define deng as the denominator coefficients in the same order as they appear in the denominator. So we had s squared, its coefficient was 1. We had 3s, its coefficient was 3. And we had 12. It is a coefficient itself, so we put 12. So we have our numerator and denominator coefficients. The next thing we need to do is to form a transfer function with this numerator and denominator coefficients. With this, we can use the TF function in MATLAB that creates a transfer function object for us. As you see, when I open the bracket, it shows me what are the inputs that I can put here. So I'm going to only input the first two inputs, the numerator and the denominator. For numerator, I want to use my numg variable that I just defined. And for denominator, I want to use the deng that I just defined as well. And they both relate to the transfer function that we saw for the simple system that we looked at. So if I run this, we see that in the command window, because I did not put any semicolons at the end of my third line, it is showing the actual output that is stored in the sys variable. So my transfer function looks 0.8 over s squared plus 3s plus 12. This is what I wanted. So this way I can check that what I have defined is actually correct. If you misplace these coefficients, your transfer function that you see here would be different. So this is a good way for you to check if the transfer function you have defined is in fact what you intended to define in MATLAB. So now that we have the transfer function defined, and we see that it is correct, we can double check with what we intended to create. I'm going to put a semicolon here, so we're not going to see the output again. And now I want to see the response of this system. So we said we can use the step function. And again, as I open the bracket for the step function, I can see the input, and I would like to input to this step function my system that I just created in the transfer function form in the previous line, and now it is stored in my workplace. So if I run this code again, it is computing. We see that it says busy here. And once it is done with the computation, it should open a system response for us. Note that on this system response, because we're not manually creating this plot or output, we do not really have much control unless we go back and try to change the view or the behavior of this plot or how it looks, the appearance. So by default, this is how we get the response. We see the title as a step response because we use the step function. We see in the y-axis we have the amplitude, and in the x-axis we have time in seconds. We see what is the value for, or what is the behavior with this blue curve for our system response. And we see that it has settled at some point, and that settling point for this system is now identified also with this dashed or dotted line. So we can see where this system is stabilizing at, or what would be the system output as it operates and eventually settles at some place. So this is a simple way of identifying or viewing the response of your defined system to a step input. Now we said this is option 1. So now that I have done this, I'm going to start creating sections. So I'm going to say sample 1, option number 1, so that I can run my code independent of one another. So I'm going to go to start writing example 1, option 2. So let's go back to the slides. So this was option 1 that we just reviewed. And this is the same code that we use. We just did not write the comments again because we were discussing them. But you can always add comments to let whoever is going over your code to know what you were intending to do in a particular line of code or in a certain part of your code. We can also use the LSIM function, which is another built-in function in MATLAB, to obtain the same response or output. So to do this, we are going to go back to MATLAB and we're going to start writing the same thing that we did, but we're going to this time use the LSIM function. Now something to note here is that when we use LSIM function, we will need to include additional. So I'm going to just copy paste the part that is the same. But in addition to having our system transfer function, when we use the LSIM function, we need additional inputs. So we need the input time or the simulation time vector. We're going to define it as t equals 0 with the step size of 0.1 up to 5 seconds. So we're going to want to do only 5 seconds of simulation here. So that will be our simulation time vector. And in addition, we need an input vector. So an input vector is what will be at any given point in time the input to your system. Now for the step, we know that the input is starting at some point and remaining that same thing. Now the unit step has the value of 1. the function 1 here creates a vector of the size input, so you can input a size here, with all values that are equal to 1. Here we want the u, or the input vector, to have the same size as our time vector, because we want at any given point in time to have an input vector or input value u. So to be able to know the size of the time vector, we can use the function size and then give the input t to the function size, and then give that size, or the output of the size function, as an input to the ones function. And this makes sure that whatever vector we get for u, which will be a vector with all values of 1, has the same size as the t vector. So if I run this section, I should see two new variables in my workspace. So I have a time variable with 501 elements. And for my u, or input vector, we see that it has the same size as my time, or t vector. This is because when we were defining our ones vector, we had the input size as t. Now to see how this u looks, if I dive into the u, you see that all the values of u are 1. And this is the definition of the input step unit, or unit step input. So now that I have defined, in addition to my system transfer function, the time and the input vectors, I can use LSIM to simulate my system. So the first thing I can get, note that here, as I open the bracket, I have one input option, but if I click here, I have another input option. So in this case, I want to input the transfer function that I just created. And in addition, I have to use my input and time as the other inputs for this system. And if I run this section, we can see the results of this to be this output. So we see that this time we have a different look, but the question is it actually a different output? So I am going to try to have a new figure. So when I plot the first one, I can get the second figure, or second plot in a new one. So I'm going to run this section first. I will get one output. I'm going to run this second one. I'm going to get another window. So now I will have a side by side. So if we look at these two, we see that the reason we see different appearances is mainly because of the scale on the y-axis. So here we have the scale, or the maximum, to 0.09. And if we were to zoom into this plot, so that the maximum is going to be 1.9, we see that we would have the same appearance as the first output that we got from the step function. So this confirms that we are getting the same output. Now, if you wanted to note that in both cases, we got an automatically generated plot. Now, if we were to try to manually plot the information, or the data that we get, or the system output or behavior, and then try to change them to whatever or however we want it to look or appear, we can try to store the output of the LSIM function in a vector that has y, which will be our output, and t1, note that this is a t1, this is not t, so I'm storing in a new variable, which will give me the simulation time that should have the same size as my output y. This ensures the output that I get has the same size as the time for the output that I get, so I can plot them properly. So once I get the y and t, so let's run this section again, we should see that we have a new variable y now, and we have a t1 now, and these two have the same size. Note that this time these two are column vectors, so they have a different dimension than the original t and u that we defined. So this is why also it is important to output the time when you're using LSIM, to have proper dimensions for your plotting. So now that I have done that, I'm going to comment these figure lines because I don't want to create more figures. And additionally, what else I can do is I can use the command close all, which will help me to close all open figure windows. So if I plot a new window or plot a new figure, it will open a new window. So I'm going to run this section again. This will help me close all open figure windows. And I'm going to try to plot the information from this output. So I'm going to plot t versus y as the output of my simulation. Run this section. And I will get the output plot. Now with this one, we can do all the things we need to change the look that we have looked at before to make sure that this figure is good enough for presentation or for other applications that we need to include in a report or show to someone else that needs to understand what this plot is showing. So a simple change could be adding grid lines, adding an X label, and adding a Y label. So if we do this and run this again, we will get a modified plot version that has the grid lines, has the y-axis and the x-axis labels, and it is more informative than the original version we got or the plain version that we got with just the plot function. Note that you could still add more things or modify all the things that are here with some of the topics we discussed before in the introduction to MATLAB. And in addition to that, there are other functions and possibilities for changing the look of your plots to make them more appealing and make them more informative to the end user or your audience who's going to look at it. So we looked at example 1, and we used two options to obtain our outputs. Now let's go back to the tutorial slides and see the option 2. So for option 2, we use the code to get the result. We then stored the outputs, and then we use that stored output to plot our results, and we said you can change this to however you want. Now suppose that the input is a unit impulse instead of a unit step at time 0. Again, we have several options for simulating the system response. So this time we are going to try to do the same thing that we did before, but we're going to do it instead of a unit step input for a unit impulse input. So let's go back to MATLAB and see how we can do this. So I'm going to start a new section. To save time, I'm going to just copy paste example 1, but now we have example 2, option 1. My system is the same system, so I'm going to keep namg, denji, and system definition the same. But instead of a step function, we have an impulse. So I'm going to use impulse function, which is another built-in MATLAB function. So with this, if I run this section, again, I'm going to use this close all in all my sections. To close all the open figures. So if I do this, I will get this plot. And we see obviously that the system behavior is different. And we see that now it is settling at the amplitude of 0. And it has a very different transient response here. So the path it goes through to get to that 0 output at the end is very different. So this would be the impulse output for the same system that we looked at in the example 1. Now, same as option 2 for example 1, we can use again the LSIM to find the same output, but for this impulse input instead of the step input. So this means that we have to define our input and time vectors again. So again, I'm going to copy option 2 for example 1, because we have similar approaches. Now here, I need to define a dt variable, and I'm going to change this step size with dt as the variable. And for the u, I need all my variables or all my inputs to be 0. So instead of 1, I use zeros function. Again, for input, we give it size of the time variable. So our time and input have the same size. But for impulse, we have only time 1, or the first input, equaling the variable 1 over our step size for our time. So this is the definition of an impulse input. We are creating this manually so we can feed it to our LSIM function. Next, we go to the LSIM function. We run our system input. We have our system transfer function that we define. We have defined our input, and we have defined our time. So we are going to use the same plotting option. So this time we directly go to storing the outputs, y and t1, and then we're going to plot them. So I'm going to run this section again. And we see that we are getting a similar appearance to option 2, for example 1. And we are getting the same output behavior as we got with the impulse that was a built-in function in MATLAB. So again, to get the impulse or unit impulse input to a system behavior, we can use both the impulse function and the LSIM function. So this is option 1, and this is option 2. Now those ones, the examples we looked at, dealt with transfer function. What if instead of transfer functions, we have a state space system model? So here we're going to look at this system creation with the state space representation. So as we can see, we have A, B, C, D matrices. And this time, instead of the TF function, which was a built-in MATLAB function that gets a numerator and denominator, we can use the SS function, which stands for steady space, and gets as input the matrices for steady space A, B, C, D, and then generates a system object for us that we can then input or give as an input to the step function or the impulse function. So let's go back to MATLAB and try this one. So I'm going to try to copy example 1. Now we're example 3. And this time I need to define A, B, C, D matrices. So I'm going to define A as given in the problem. So for this D matrix, you can use the square brackets or drop them because it is only one variable or one element. This basically is not a matrix, it's a scalar. But either or way, MATLAB will work with it. We can see that it is giving us a warning that using a bracket is unnecessary. So you can just click on fix and have them removed. We're just keeping them for consistency of the definition of the matrices, but you don't really have to do that. You can just use the D as a scalar with a 0 value. Now this time, instead of the transfer function, we use the SS function. And as we said, the SS function gets A, B, C, D matrices for our state space representation and creates a state space representation system for us. So we can see that we can have the step, again, an input system that we create from a steady space form now as an input to it. So I'm going to run this section this time. And we are getting this system output. Note that this is the same output that we got to our first example. So what we see is the state space representation of our first example that we looked at and also used again in the second example. So we're using the same system, different representation, and we're seeing that we can get the same output regardless of how we are looking at our system and how we are using the different techniques to plot the output or obtain the output of this system. The other thing to note is here I did not put a semicolon at the end. So we see that our system is created and the output is shown in our command window. So we see that in the option that is created, in the system that is created, we can see the A, B, C, D matrices, which shows us that we do have a steady space model, and it also tells us that it's a continuous time steady space model system that is stored in this sys variable. Additionally, if we want to use impulse, we can also obtain the impulse as a system output to see what would be the behavior of our system for impulse. So we get an error message because I spelled impulse wrong. We run this again. So we see that for the impulse, we again get the same output that we got from the previous examples from different options that we looked at. So again, it shows that we can use different ways, different representations, different functions, different methods to be able to obtain the same output for the system to a certain input. So we use a steady space representation, and we used again the step and impulse functions to be able to obtain the system output or behavior. Notes on a step and impulse. Step and impulse assume that the system has 0 initial conditions. Of course, if you're using a transfer function, it has 0 initial conditions by definition. That is how we can actually form our transfer functions. But what if you have a system with non-zero initial conditions? For a system with non-zero initial conditions, you must use a state space representation. That was the last example that we looked at. Now there are two options. You can use LSIM. We looked at the LSIM, but we looked at the LSIM without an initial value or initial condition, or you can use another function called initial. So you can use LSIM or you can use initial. So for the LSIM, you can add an extra input that will be your initial condition. For initial, you only need to give your system, your initial condition, and your time. And in both cases, you can store the system outputs or the function outputs, which will be your system response, in magnitude and time, similar to what we have been doing in the previous examples. So let's see how we can use these. We're going to look at example 6.1. This figure shows the simple series RL, which is resistance inductance circuit. Use MATLAB to determine the current IT and the resistor voltage EO if the voltage input ENT is 1 volt step function applied at time t0. So we have a 1 volt step function as input applied at time 0. The current is initially 0, so we have an initial 0 current, and we have the values of the inductor as 0.1 henries and the value for resistor as 1.6 ohms. So let's see how we can get to the solution of this. Before anything, we need to find what is the equation that describes the system, or what is the system model. So we have a source input, we have one inductor, we have one resistor, we have clockwise current direction, and we also have the resistor voltage defined as EO. And this is why, like, output voltage. So we want to actually look at the current and the voltage of this system, or the resistor over time. So let's get to the modeling. We have one loop, so we can write the KVL, and we have one storage unit or energy storage unit, the inductor. So we can write the fundamental ODE for this. In the fundamental ODE for this, we have elements that are not allowed. So to replace those elements, we can use the KVL because we only have one loop. There are no nodes, so we don't use KCL. And then once we are substituting everything, we are able to write the system model for this circuit as Li dot plus Ri equals ENT. So we have our important variables and their dots in the descending order of dots on the left-hand side and everything else to the right. Note that I is our important variable for this system, and we have L and R values given to us, and En is our input to the system, which we're also given how that should behave. Now we need a transfer function. Remember, for transfer function, the assumption is that the initial conditions are 0. That is not always true, but in this example, since we have no voltage, and with no voltage there is no current, we can apply the transfer function because we will have a 0 initial conditions as well. Now, we use the D operator on the equation we obtained in the previous example, or equation 1, and we get LDI plus RI equals En. We can collect the I terms, so LD plus RI equals ENT, and then forming the output over input, we get IT over ENT equals 1 over LD plus R. Now, changing the D operator to the Laplace variable S, we can readily obtain our transfer function. So IS over E in S in Laplace domain equals 1 over Ls plus R. So this is our symbolic transfer function, but we also have the values for L and R. So we can actually go ahead and substitute the values for L and R in our transfer function, and we can obtain I over E in S equals 1 over 0.1S plus 1.6. Now, because the input voltage E in T is constant with magnitude of 1, we got a 1 volt input, we can use the step function to obtain the unit response. To do this, similar to what we did for our example 1, we can define the system using a transfer function, define the time that we need to get the system output, and then store the system output in this step. Note that in the example we solved earlier, we only gave input system to the step function. Here we are also inputting the time vector that we need the step function to use to simulate our system, meaning that now a step function will try to obtain an output for the system at any of the elements of time in the time vector, instead of automatically defining the time vector for us or for the simulation. This can particularly be useful for more complex systems, or if you want your system to have a certain step size and a certain start and end time for the simulation. After we finish this, we also know that the output or the voltage for the resistance from the Ohm's law is equal to the resistance multiplied by the current. Now, if we obtain the current in this step as an output of this simulation, it will be a vector, and if we multiply it by the constant value of the resistance for the resistor, we can obtain the vector EO, which will be the voltage of the resistor at any given time in the simulation. Now let's go to MATLAB and try to implement this. So we are going to use example 1. But this time we're working on example 6.1. We don't have options for this one. So here we can either define, again, numerator and denominator. So our numerator will be 1 this time, and our denominator will have 2 elements, so 0.1 and 1.6. We can define our system with transfer function, numerator and denominator. And we also need to define the time vector, that is 0 with a very small step of 1,000th and 0.5 as our end time. And here we also need to input time, and we need to store the output of this simulation into respective variables. So once we do all of this, and let me also add CLC and clear, so I can clean my workspace and my command window, and all we see there will be from this section only. So once I run this, I see that I have my I as an output, T1 as an output, and my system, which is a transfer function. So the next step is for me to be able to plot this. Additionally, we need to create EO using the Ohm's law as RI. We already have I. So if I run this, now we see EO should have the same size or dimensions as the I and T1. So with this, I should be able to plot my results. And I'm going to use plot T1 and I. I'm going to add grids and X label of time, seconds, and Y label current amps. So if I run this, now I should get my system output, which is the current over time from 0 to 0.5 seconds. And this is calculated based on the time input I have given with the step size of 0.001. Now to see how this might potentially change, if I change the step size to be 0.1 and run this simulation again, we see how that my output is now calculated at only 5 points for this system, and how that this is no longer a smooth response, not because the system is behaving this way, but because of how I have simulated my system. So we have to always make sure that we do have a small enough step size for our simulations to capture the actual behavior of our system. So in this case, we see that if we use a 0.01 step size, we would still capture the proper behavior of this system. And if we didn't input this system as time, the step function would automatically use a step size that would be appropriate for capturing the proper behavior of this system. And then we could store that value in T1 as an output of the step, so we could plot our results. So this is our current. Now, if we wanted to also see the output or the voltage for the resistance, we need to add another plot or add a subplot. So here I'm going to use the subplot with 2 rows, 1 column, and I'm going to plot the voltage in the second plot. So if I run this now, I should get a plot that has the current and the voltage for this system. And we see that since they have a linear relationship between the two, so basically E is just a multiplication of a constant by I, they have the same pattern of behavior, they just have different amplitudes. So this shows the behavior of my system for this system with initial conditions, without initial conditions, and it was an actual system that we were able to find the system model, and then we could use that system model to form our transfer function and obtain the results and plot the results to step input. So these are the outputs for our system, and we see that again they have the same pattern of behavior, but they have different amplitudes. Remember that we can also obtain the same results with LSIM function, similar to the first two examples that we did, but we're not going to do it here. If you would like to, you can do this on your own and get some practice and then compare your results. Next, we get to example 6.2. This figure shows a three-way spool valve used to meter flow in a hydraulic system. And this equation, equation 1, is the mathematical model of this valve. Use MATLAB to obtain the response of the system if the applied force Ft is a pulse function that steps up from 0 to 12 newtons at time t equals 0.02 seconds and it steps down to 0 at time equals 0.06 seconds. The spool valve is initially at rest. So for this system, we are already given the system model in this form. And we are asked to model this system or get the response of this system using MATLAB. But this time we have an input that we haven't worked on before. So it's a system input that goes up and then goes back down. So it is a transient input. Now, quickly to see how the system equation or system model is obtained, we have a mass spring damper system and we have an input. So free body diagram, we have a mass, the force from spring and the friction, that is our damper. And then we have the input Ft. So using the sigma F to the right positive, we get everything equaling summation of all the forces equaling my double dot. Moving all the important variables in the descending order of the dots to the left, everything else to the right, we obtain our system equation. And if we input or substitute the system parameters, we would get the same equation as we have or given in the problem. So these basically are the system parameters that are replaced by the symbolic variables m, b, and y. So this is just a quick review of how this system equation or system model is obtained. So to get that, we need m mass to be 0.0.4 kilogram, b to be 16, and k to be 7,000. That is just the one-on-one comparison of the elements and the final equation. Now yt is in meters. Assume there are no hydraulic fluid pressure imbalance on the valve and the flow forces are neglected. The system is initially at rest, that is what is told to us or given us. So y dot naught equals y naught equals 0 at time 0. And the force steps from 0 to 12 Newton at time t equals 0.02 and then goes back again to 0 after some time. So we first need to find our transfer function. So to find a transfer function, we can use the d operator. So we find the d operator equation, collect the y terms, form the output to input fraction, and then replacing d by s, we get our transfer function. Again, we can use transfer function because the problem tells us that the system is initially at rest, so we have zero initial conditions. So now that we obtain the transfer function, because we have a transient input, note that our input is going up and then going back down to 0. So it is 0 initially, then goes to 12 and then goes back to 0. We must use LSIM. We cannot use the step or impulse because those ones have predefined elements of ones and zeros. And here we have a different pattern for our input. So this time we need to go ahead, again, use our system inputs, system transfer function, and then obtain the results and plot them. So let's go back to MATLAB. And then we will have a similar example to example 2. So I'm going to copy this one this time. This will be example 6.2 with no options. Now that we do this, so this time we have our numerator as 1, and we have our denominator as 0.04, 16, and 7,000. So this will be our system. We can for the transfer function using the transfer function. And here we will have our t as 0, 0.0001 to 0.1. So this will give us enough accuracy to be able to fully capture the behavior of our system. Again, you can play with the step size for your simulation to see which one gives you a better resolution for your output without sacrificing the actual output that you should be getting. So it is a trade-off. Now this time we have our input as f, so we'd use f 1 to 200 equaling 0. Then we have f of 201 to 601 equaling 12, and then 602 to 1001 equaling 0. So the values we are inputting in this f are basically the indices of the elements in our input function. So from 1 or from the 0 second to the 0.02 second, we have input of 0. Then between 0.02 and 0.06, we have 12 Newton as input. And afterwards, we have again 0 input. So we are creating our input manually. If I were to quickly plot our f versus time, we would be able to see, so I'm using return so that nothing after this is actually computed. So we are going to only see our input. Looking at the input, we see that it goes from 0 to 12 Newton, stays there, and then goes back to 0 again. So now I'm going to use LSIM. So for LSIM, I have system input. My input this time is stored in f variable, and my time is in t. I'm going to store the output as y and t, and I should be able to plot my output with t1 and y, but also I want to use subplots to be able to first see my system input, and then right below it, see my system output. So here I will have T1, you can use just T and F. For output, we have T1 and Y for output, and I'm going to run this, and this is what we get. So we can clearly see that the input is now a step and then goes back down, so it's a transient input. And we see how the system is responding to this input. Exactly when the input is going from 0 to 12, we see that our system is reacting and trying to go to another value, but we see that it has an overshoot, so it goes above that value and then oscillates a little before it settles down at the value for some time. And as soon as the external input is removed, so it goes back to 0, we see again the system responds to that and goes down. It now undershoots the value of 0, but it oscillates and eventually goes to the value of 0. So this shows us how the system is behaving exactly as it should to the input, and plotting these input and output below one another helps identify the trend lines for our system. So this can be a good practice for you if you want to see your system response to a particular input, or whether it's input and multiple outputs and how all of them are behaving. Using subplot can help you see all your outputs and inputs in one single plot or figure and then make decisions or have particular analysis for your system. So this is also the same result that we obtained from our system. And in this case, if we go back and see the resolution that we have here, if we change this resolution or step size, we have to now change what we are using for our indices because they are related to that step size, because depending on the step size, the size of your time variable or vector is going to change, and then your input vector must have the same size as your time, so you have to adjust these indices to make sure that they are on the same alignment as the input time so that you won't get error messages from MATLAB. So in this case, let's just try reducing it to 0.01. That means we have to divide 10 from these. Then let's run this. So now we see that we do have an error message because we have our t as 101 and then our f, it has 1001. So we need to clear this. That is the reason we have to clear our workspace. So whatever was stored there before is now gone. And now we can see the system response looks almost similar, but the issue appears here in the input. If we take a closer look, if we try to zoom in, we see that the step is not actually in a step, it is a ramp. And that is because of the resolution that we used for our simulation. So we can see that we needed that very small step size for this system behavior to be exactly a step up and then a step down. Otherwise, even though we get a similar system output, it is not exactly how the system should be behaving. And also we see some non-smoothness in the system behavior or system output, again, because of that resolution that we just reduced. So this shows that we need a really small step size for our time as 0.0001 that we used initially to be able to get proper system outputs. And that is all for the review of some examples using MATLAB for control applications.